Sorry for the delay. Start now. Now we are starting. It is recording. So basic premise, I think everybody knows, but I'll just repeat it. Okay. When you are imagining the thermodynamic process to be happening, just think of a cylinder. Okay, in which there is a, say, a piston. I hope you got it. So this is the system. This gas in here is the one on which we are doing work, or it is doing work, whose internal energy is getting measured, and the heat is being supplied in. Right? You understand that, guys? If you have any doubt, you ask. Okay. If you don't know what are the terms and what is happening, obviously you will start facing difficulties. So for me to understand whether you get it fully or not, what is Q, guys? What is Q? You can write as delta Q also. I'll be writing as Q only. So what is Q? What is Q?
Heat supply.
Yeah, heat given to the system. Okay. Heat supplied. If I am putting in some, say, 100 joules of heat, if it is going in, then Q is plus 100. Okay. If heat is coming out, then Q will be minus. Right? Is that clear? Is that clear? It can be like the chamber is too hot and it is giving out heat. The walls are not adiabatic. The heat can flow out. If it is giving out heat, then the Q will be negative. Is that clear, guys? Everybody understands that? Everybody understands?
Yes, sir.
Okay. Next important term is internal energy. U. So what is U? Anybody? What's the measure of internal energy? What is internal energy comprised of? What do you mean by internal energy? Yes, yes, yes. Fast, fast, fast. Anybody? Somebody? Yes, guys. Each molecule is moving, right? So it has got a certain kinetic energy, right? Right? Those molecules can be of various shape. It can be there can be two atoms, diatomic molecules can be there, right? So apart from moving, it can be rotating also, and we know that due to a particle rotating, it will have rotational kinetic energy. Due to its translation motion, it will have translational kinetic energy, right? And on top of it, these atoms may be vibrating also at their own place. So due to the motions, various kind of motion of those atoms and molecules, they have got kinetic energy that is called your internal energy. Is that clear? Is that clear, guys?
Yes.
Here we are not talking about this thing was kept at so much of height, so its potential energy is high or potential energy is low. Not at all. Is that clear, guys? Is that clear? What is internal energy? The net kinetic energy of the molecules, of all the molecules together. Okay. Now we have already in kinetic theory of gases, we have seen that velocity square is proportional to the temperature. Right, people? There is a certain derivation in kinetic theory of gases. Right? Temperature is a direct measure of the velocity. Okay. Hence, this internal energy will be dependent on the temperature. Whatever is the temperature, how you came to that temperature, you came from a very low temperature to that temperature, you went from a high temperature to that temperature. It doesn't matter. If the sample is at, say, 40 degrees Celsius, then it has got a certain internal energy. Is that clear, guys? Is that clear?
Yes, sir.
Okay, so the details are at that temperature. Some of the molecules will have this most probable speed. Some will have low. Some will have high. And Maxwell distribution graph is there. This and that. But the sum of all the kinetic energy is your internal energy of the system at that time. Okay. So, and the third term is that this piston can go up or down, right? If it goes up or down due to some force, say from inside there is a force, due to the internal pressure there is a force and the piston goes up, then what is happening? There's a force, there's a displacement. So what is happening? There is work done. Okay. So this is actually your engine. So it is the work done by the engine, right? The work done by the system, we say, right? If it goes up, if there is a force from inside and it goes up, then there is a work done by the system. Is that clear? So the third term is work. Okay. That work, or we'll be just writing W for it, is same old thing. The force times the displacement integration. Is that clear? But force happens to be pressure into area. Say the pressure is P, pressure into area dot dx. Then this area into the displacement dx is the change in volume. Is the change in volume it creates. That will change in volume, right? So this can also be written as P dot dv. Hence, we'll use the work formula as P dot dv in this chapter, which is ditto same as F dot dx. Is that clear, people? Is that all okay? Any doubt in all these three terms? Q, U,
No,
and W? Hmm? Any doubt? Now, there is a fine point. Now, that whether you understand fully or not, it is hardly going to matter in you being able to crack a certain question. I'll just put the fine point over here. So, try to pay attention to this point which I'm proposing now. There is a cylinder. That's the piston. Total energy is conserved. Okay. We are not talking about mass becoming energy or energy becoming masses. Okay. We are not talking about that yet, at least not in physics at all. Okay. So the heat given in is suppose Q, and somebody pushes the piston down. Somebody pushes it down due to the external pressure, which is say atmospheric pressure or whatever pressure from outside. There is a push down to the piston, and the piston goes down. So work is done on the system. So what is positive? Work done on the system is positive. In this case, when the volume is reducing, on the system is positive. Okay. So there is some work done on the system. Let's assume that 100 joules of work that has been done on the system. Similarly, heat is given, so Q is positive. Heat is given into the system. So let's assume 200 joules of heat was given into the system. Okay. So much of energy is given, 100 as work and 200 as heat. So what is going to happen to the internal energy, people? What is going to happen to the internal energy? Internal energy is going to rise, right? Rise in internal energy. Okay. When we say change, it is change in physics means rise. Okay. It is final minus initial, from initial to final. It is always rise. Okay. Change doesn't mean you can subtract anything. Final minus initial is your change in physics. Okay. This delta means that. So rise in internal energy is naturally equal to how much of energy is supplied as heat plus how much of energy you supplied as work. Right? That's your first law of thermodynamics. Any doubt about this, guys? Any doubt about this? Now, in physics, what happens is we are always talking about a quasi-static system. That means The system is going very slowly, such that we will say that the external pressure and the internal pressure was same, almost same. Okay, it's going very slowly down. If there was a big difference, then only it will go very fast down. Okay, is that clear? So if we consider the force from the inside, then the force is up, wherein the piston is going down. So work done by the system is negative. Work done on the system, work done on the system is positive in this case, wherein the volume is reducing, the work done by the system is negative. Is that clear? So work done by the system is given by minus 100 joules in this case. Is that clear, guys? Is that clear? And this formula of change of internal energy will be heat supplied, that you supply a certain amount of heat, 200 joules of heat, minus how much is the work done by the system. The system does some amount of work, then your internal energy will be not that much of rise. It will be minus how much is work done by the system. So this is the format we write in physics. Okay, there is no difference between the two. They are ditto same, provided we assume P external is equal to P internal. Okay, there's a big assumption. That's a quasi-static process. Is that clear? Thankfully, all our JEE questions and everything is, or NEET questions or whatever comes in physics is quasi-static. Okay, from this chapter. Is that clear? So we can use the two formula interchangeably. So in physics, we generally use this formula, wherein one may argue that this is the better format of using, that total energy supplied is the change of internal energy. Okay. So when such cases are there that outside is vacuum and inside is not vacuum, there's a big pressure difference, then we have to use it very carefully. Okay. There are concepts over there which in this class, today's class, we are not going to discuss. Okay. Is that clear? Do you understand the difference between the two formula? I'll repeat, both the formula are same. Both the formula is same. Okay, if I apply the top formula, my answer will come as 200 plus 100. If I apply the bottom formula, my answer will come as 200 minus 100. Okay, so there is no numerically, they are not numerically different. Okay, they happen to be different only when your P external and P internal will not be changed, will not be same. So you have to be careful over there. So I hope you understand these three terms very properly. Okay, so from henceforth, we are always going to use the formula heat supplied is equal to, it will increase the internal energy, more heat is there, then with that heat, the system will do some work done by the system. Work done by the system is positive if volume increases, and work done by the system is negative if volume decreases. Any doubt, guys? Any doubt? Any doubt? If you have doubt, ask right now. Any doubt? People?
No, sir.
Sure? Okay. Okay, somebody tell me if uh, heat supplied was 200 joules, work done by the gas, was 300 joules. Is it possible? Is it possible? Is it possible? Fast, fast, fast. Sleeping people, fast. Is it possible? Hmm? Well, bhai, possible or not possible? Say something, man. Only two answers are there. Possible or not possible. Hmm?
Not possible.
Huh?
It's not possible.
It is possible. Okay. So if you supply 200 joules of heat, if the system does 300 joules of work, in fact, if you don't supply any heat, still the system can do work. From where will it do work?
An
From
external
its
force.
own pool of internal energy. Okay. Internal energy is like a very, very big number. Okay. Hmm? We are talking about change of internal energy in the formula. So it will expend from its own internal energy. Okay, it has got a lot of heat in itself. Unless until it is at absolute zero, then it has no heat. Internal energy formula is dependent on the temperature. Due to the temperature, it has got heat. So from the formula, we straight away put the formula and check what happens. Plus work done by. So this is 200 internal energy. Work done by is 300. So you get that internal energy change will be minus 100. We need to say the internal energy will reduce by 100 joules. Is that clear, guys? You understand these things? Hmm?
Yes, sir.
Okay. Now there are few all-time formulae which is always valid. So first I will list that. Okay. I will list it. One is in a certain process, if you are supplying heat, okay, this is all-time formula number one, I'll say. Okay, if you are supplying heat, and the temperature goes from T1 to T2, then no matter what is the process, it's an adiabatic process, isobaric process, isoporic process, whatever is the process, is some polytropic process, your heat supplied is given by Ms delta T. In gases, instead of using mass and specific heat capacity per kg, we use per mole. So N C delta T. This is an all-time formula. Is that clear? This is very, very important because it's not very clearly stated in places. Okay, formula can be used anytime in all situations. Okay. Valid in all cases. Is that clear, guys? Is that clear? But using this formula for gases is very tricky. For liquids and solids we use. Can anybody tell me why for gases it is not so easy to use? Can anybody tell me why for gases it is not so easy to use? I'll explain over here. Very, very, very silent crowd, man. That's too bad. Too bad. Say something, something. Say wrong, big deal. If you become quiet, your mind goes, I mean, it slows, it doesn't absorb that much. If you are active, it will absorb more. Okay. Say this was at 40 degrees Celsius. Say this was also at 40 degrees Celsius. I have put a lock over here. The piston cannot rise, and I give them heat, say Q1, such that the temperature goes up to from 40, it goes up to 60 degrees Celsius. Here I have not put any lock and the piston goes up while I supply heat. Piston has gone up while I supply heat. Q2, and the temperature has become what? 60 degrees Celsius. Do you think Q1 and Q2 is same? According to this all-time formula, Q1 will be equal to NC into change in temperature, 60 minus 40. Okay, according to that formula, Q2 will also be equal to NC 60 minus 40. But I clearly know that the heat should not be same in both. Can anybody tell me why heat should not be same in both?
Sir, is it because the volume differs?
Yeah, so
Sir, if we use the ideal gas equation, will we get for a fact that it cannot be the same?
like that, ideal and this and that. Ideal or real or जो भी है, but volume differs, so
Sir, is there a work done?
absolutely right. Okay, we are thinking of only three things: Q, internal energy, work. Internal energy only depends on temperature. In both cases, internal energy change is ditto same. Why? Because the temperature change is ditto same. Okay. Just remember, internal energy is a direct mapping on temperature. Is that clear? But in the second case, there is work done by the system. That means I gave heat and the system did some work also, apart from increasing the internal energy. Therefore, I must have given more heat in Q2 than in Q1. And one can imagine if the lid is kept, therefore, pressure cooker and all is a very efficient cooking because of many factors. One of the factors is that it's not, the system is not doing any work, so all the heat is getting consumed in increasing the kinetic energy of the molecules inside the system. Okay, so in this Q1, heat is being used in increasing the internal energy. Here, it is being used to increase as well as go up. So what about this all-time formula? So where am I wrong? Where am I wrong? I said this is always valid, okay, with a double, triple, four ticks. The point is the C value for each process, whether you are doing isobaric, isochoric, some polytropic or this or that or some random process, for each process C is a different value. C is not fixed. Unlike for liquids and solids, it is slightly it changes, but we take it almost as constant. The specific heat capacity of water is 1 gram per, 1 calorie per gram. So that we take it as a constant. Okay. But for gases, it is different. So what should be written over here? In the first case, volume was not changing. It is NCV into 60 minus 40. In the second case, volume is changing. Perhaps it is going under constant pressure from outside, atmospheric pressure. So we can say NCP if it is a constant pressure process. And we know that Cp is more than Cv value. Okay, that's another thing that you'll learn. Okay, Cp is more than Cv value. So heat is here more. But I'm driving the point again back that this formula is the all-time formula provided C of the process is known. C of the process. C of the process is known. Which one may not be knowing. Is that clear, guys? Is that clear? So if a C of the process is known, you don't go for this plus this. You can directly apply N C process delta T is your Q. Is that clear, guys? Is that clear?
Yes, sir.
Yes, sir.
If the C of the process is not known, then obviously you'll check whether you can calculate work or not, whether you can calculate internal energy or not. Okay. So the next one would be another formula which is always valid. Okay. What is that formula? Delta U is equal to N CV T delta of that, and if the number of moles, if the composition is not changing, if the molecules are not breaking or something, then we can write it as NCV delta T. Okay, so in physics we can always use this. Okay. Is that clear? whether it was a isothermal process, whether it was a isobaric process, delta U is equal to some constant into T, and that constant happens to be CV. So don't get confused that this formula is only valid for isobaric process. Are you understanding? Are you understanding? So one may write it as N FR by 2 into delta T just to show that it's a constant. R is a constant, 2 is a constant, F is degree of freedom according to the structure of the molecule. So that this is a all-time formula, valid in all processes. Delta U is so much in all processes. Is that clear, guys? Is that clear?
Yes, sir.
Okay. So any question, you will use these all-time valid formula. The third time, all-time valid formula will be PV is equal to nRT for ideal gases. PV is equal to nRT. Now, if it is adiabatic, you will say PV power gamma is equal to constant. Yeah, well and good, but this is still valid. Okay. On top of it, other formulas are becoming valid is another story. Is that clear? So this is valid for adiabatic, non-adiabatic, this case, that case, all cases. PV is equal to nRT. So this is the premise that you should be knowing that these three formulas work all the time. Is that clear? Is that clear? Is that clear, guys?
Yes, sir.
Okay. Now coming to PV diagrams. If I make a PV diagram, say I make some random thing, okay, like this. At any point, what all can I read? Tell me what all functions can I read, or what all variables, or what all characteristics can I read? Say something at this point. I can read what? The pressure, right? I can read the volume, and what else I know from here? I know the temperature also. How do I know the temperature? Because PV is equal to nRT is always valid. Okay. Assuming number of moles is given to you. So PV is equal to nRT. Using that, PV will multiply and we get the temperature. Is that clear, guys? In a PV diagram, all three readings are there. Okay. So in fact, VT diagram, PT diagram, or PV diagram, any two is used. The third reading is also there using the PV is equal to nRT. Sometimes questions come, convert this diagram to a PT diagram. Okay. Is that clear that we have all readings? Is that clear, guys?
Yes.
I don't think people, okay, just tell me this temperature, say T1, or this temperature T2, which is higher temperature? Which is higher temperature, T1 or T2? Loudly, loudly.
So the T2.
T2 is higher. Why? Because we'll just put P into V. Pressure is same, but volume is more, right? So PV multiplication is more over here, right? Right?
Yes.
What about this T3?
It's lesser.
It's less, right? What about this T4?
That's also
Yes.
less.
Quite less, right? E is also less, V is also less, right? So looking at the diagram, you should be like having some idea. Oh, that's a high temperature, man. Oh, this is low temperature. Get the point? Is that clear? Since you are giving me so many temperatures, can you tell me another T1 temperature? Where will it be roughly in this zone? Where will be T1 or another T1? Say I reduce the pressure a bit, but the volume has to increase a bit, right? So then the
Yes, sir.
multiplication remains same, right? I reduce the pressure more, volume has to increase even more, right? It comes like a curve like this, okay? What are those curves called? Isotherms. Is that clear? If you are going like curves in this kind of curves, this will have all same temperature, T1, T1, T1 everywhere. Because the PV multiplication at any given point will be same. It will be like a hyperbola, those who are doing maths. Okay? Okay? Rectangular hyperbolas are of the format of xy is equal to some constant, right? Right? So it is the PV is equal to a constant. So, anyways, so if this is T1 and this is T2 isotherm and this is T3, which is the highest among the three temperatures? Which is the highest among the three temperatures?
A1.
T1. Okay. So I hope everybody is now very clear. Okay. Just to test you, internal energy here at point A is more or internal energy at here, point B is more? Where is the internal energy more? Where is the internal energy more?
Same.
It's same, right? So internal energy is direct reading of temperature, right guys? Same temperature and same internal energy. Is that clear? So if you get a diagram that, okay, a process went from here to there, will you be able to comment whether the internal energy increased or decreased? You should be, okay?
Yes,
You say,
sir.
oh, temperature decreased, so internal energy decreased. Is that clear?
Yes, sir.
If it went from here to there, you say, oh, temperature increased, so internal energy increased. Okay? Now, I think some of you are understanding, so I'll just show you one more thing. If there is no change in volume, then how much is work? How much is work?
0.
0. Is that clear? Is that clear?
Yes, sir.
Because work was nothing but P dot dV, pressure into change in volume, okay, integration, which is not there. Change in volume is not there, then there is no work. So I'll show you why change of internal energy formula was NCV. Why not some other constant, but CV into delta T. Okay. See, I'm going from here to there as a temperature, or I'll go from a lower to higher temperature, like this I'm doing, here to there. First of all, does it matter in the change in the internal energy whether I went that way or I went this way? Will it matter? Change in internal energy? No, it will not matter.
No,
It's
sir.
simply directly NCV into change in temperature. You went which way, it doesn't matter. So it is called a state function, where you are, not a path function. Is that clear? Is that clear?
Yes, sir.
Okay, if it was a path function, then if you go like this, it will give some other answer. If you go like that, it will give some other answer. I hope these things you understand, right? Okay. Initially,
Yes,
it looks like crazy. What the hell state function? What the hell path function? Okay, but slowly, it should become a simple language for you. Okay. Now, why I know that internal energy change is some constant into change of temperature. But why the constant is CV is quite easy to do. What I'll do is, I will first go like this, because I can choose any path. I'll go like this first. Okay, and then I'll go like this. Okay, and I'll ask you the easy one first. How much is the change in internal energy here? In the second path, that's 0. You guys just not told, right? Because there is no change in temperature, right? From here to there.
Yes.
Any doubt? So the total change of internal energy from say point X to point Y is same as change in internal energy from here to there up, right? Right?
Yes, sir.
And what is this process? Isochoric process. I've got straight up without changing volume. I can use a law. What is the law? The law is always valid. Plus work done by the gas. This law is always valid. And to calculate this internal energy, I'm going to use this law. Is that clear? So what all I know in this equation? What do I know? Do I know this? Do I know this? Work done by? Do I know that?
Yes, sir. It's 0.
It's 0. 0. Do I know this? Very fortunately, I know because I gave you an all-time formula for that. Okay? I gave an all-time formula for that. Right, guys? What is the all-time valid formula? All-time valid formula for that is N into C of the process, and I've deliberately chosen an isochoric process, so CV and CV into change of temperature using this all-time formula. And hence I get this. Is that clear? That delta U is equal to that. Okay? From here to there, and there to there is 0. So for the whole process, for this whole red thing, delta U will be N CV delta T. We need to say whichever way I went over there, answer will still be same. And then here you digest it after some time. Okay, I just told it because I thought some of you are getting it. Okay. Otherwise, what I want you to remember is this is a all-time valid formula, is irrespective of the path. What the point, guys? What the point? What the point? Okay. These things you should be like always indulging and thinking yourself all the time. Okay. Always put your thinking cap on when you are studying. That makes your study easier. Can I ask one question only? I'm not doing all the processes and systematically I'm not yet covering your work and all. Okay, I'm making you easy with the diagram. Okay, there's only 3 or 4 basic premises which you should be knowing to answer my question. One is what? Obviously the thermodynamics first law, delta U plus W by. Work done by is positive if volume increase or decrease? Increase. Is that clear? Number 1. Number 2. Number 3 is change of internal energy is always straight away a measure of change of temperature. And number 4 is how to read temperature in the PV graph. How to have a rough perception of read temp in PV. If you guys are able to do this question, I'll be so happy. Okay, because I'll tell you one thing. Whenever there is a new physics teacher I have to take or something, and they say thermodynamics, I ask the diagram which I'm going to ask you, and ask the same question which I'm going to ask you. If they mess it up over there, I know that they don't know anything. Is that clear? Is that clear? If you are doing it, you are better than all those various coaching institute teachers saying that they are teaching for so many years and not knowing the super basic also. So you'll be better than those. Okay, so take it as a challenge. It's quite simple, I'm telling you, quite simple. So all 4 is understood. Any doubt in these 4? If you have any doubt in these 4, you will not be able to answer. Shall we start? Yes, guys?
Yes.
Could you go to 4th one?
Yeah, reading temperature in the PV graph. How do you read? We were just doing it no, somewhere. Oh, I deleted that slide. Okay. Like I showed, no, what is isotherms, right? This temperature will be all same, T1, 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 right?
Yes, I got it.
This will be T2, T2, T2. This should be lower than this. This is higher because the PV multiplication is higher over there and PV multiplication is lower over here, right? Is that clear? I'm in a class. I'll call you after class. Okay? Okay, guys? Is that clear? If you have further doubt, ask me. But once I put the question, please don't ask any doubt. Okay? Anything in this four, it's like a small puzzle you have to do.
So the third one.
Third one means increase in internal energy is NCV. N and CV are constant. Okay, you don't have to bother about their values. Into increase in temperature. If temperature increases, internal energy increases. If temperature reduces, internal energy reduces. Is that clear?
Yes.
Okay, shall I ask the question now?
Yes, sir.
Okay. I know you guys are good. After answering this question, you straight away apply as a teacher's job in various institutes and start on them. Okay, say this is a certain cyclic PV diagram. Is that clear? This point is A. I'll make slightly bigger so that it is. Since there is no time, I'm not going to explain why this adiabatic process is steeper than the isothermal. I guess some of you would be knowing already, but anyway, that is beside the main point what I'm going to ask. This is point A. From A, it went to B in a isothermal process. Now, if you don't know the meaning of what is isothermal, that you can ask. Okay, there is no shame in that because there is no logic in the name. Isothermal means temperature is same. Is that clear? Is that clear? So this A to B line happens to be isotherm. Okay, and B to C is obviously not an isotherm because you can see that it is deviating from the curve of the isotherm. Okay, B to C is an adiabatic process. Okay, what do you mean by adiabatic? Anybody? What is the adiabatic process? Anybody? Again, it's a term, so you can totally ask what it means.
When heat supplied is 0.
Yeah, when the heat supplied or rejected is 0. Okay, there is no heat supplied or rejected to the system. No heat supplied or rejected to the system. This one is isobaric. Obviously, you can see the pressure is not changing. Isobaric means pressure not changing. And this one is isochoric, meaning to say volume not changing. You can see that isochoric. Is that clear? Now the question is, if in the first process, it is called Q1 is the heat supplied, okay, it's regular terms. Delta U1 is the change of internal energy, meaning to say rise of internal energy. And W1 is the work done by the gas. You have to comment on the Q, delta U and W value for all the processes, whether they are positive or negative or 0. Is that clear? In front of them, you have to write positive, 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 something like that. Is that clear? Is that clear? Is the question clear, guys? Is the question clear? And the only requirement is the 4 things I've given on the side. Is the question clear? Is the question clear?
Yes, sir.
Yeah, then do it. Once you have done this, I will further ask the further questions. Okay. Done. I think identifying work is quite easy. Identifying delta U is also quite easy because you just have to see whether the temperature is increasing or decreasing. And then you can combine the two using the first law of thermodynamics and figure out Q. Yeah, so who is done? Who would say any one process? There are some 12 items over there. Any one can call out any one item. Okay. And I hope 12 different people call out 12 different items. Like somebody want to call out delta U1 is positive or negative. W1 is positive or negative. You can just speak up your name and speak out. Yes, people. Yes. Anybody? Anybody? Somebody?
So is delta U1 negative?
Speak out your name first.
Sanika.
Anika. Which one you want to say?
So delta U1.
Delta U1. Okay. What do you say about it?
So it's negative.
Is? Loudly is? What happened? Among 12, you chose one and then you stopped. Is what? Is? Yanika? See, 1/3 chance of you getting it right, man. There are only 3 choices. Anybody else wants to speak up? Anyone?
Sir, could I try?
Yeah. Which one? Name?
Sir, John. Delta U1.
Delta U1. Yeah, okay. First, Janvi, you tell me to see delta U1, what are you seeing?
Temperature.
Absolutely right. Okay, that's the only thing you have to see. Is the temperature increasing? Is the temperature decreasing? That's the only thing you have to ask yourself. Okay, guys?
That's since it
Yeah.
then there's
Huh?
temperature.
What?
Sir, since it's isothermal, the temperature is constant. So delta U would be 0.
Yeah, no change in temperature, no change in internal energy. Any doubt, Anika? Any doubt in this? Why were you thinking it is negative? As simple as that. Okay, you identify whether the temperature is increasing or decreasing and just comment on the answer. You can do it for all. Okay. Even easier is work. Because temperature you have to at least, read the temperature. Well, reading volume is even easier because it's a PV diagram. So anybody can tell me about work?
Excuse me,
W1
sir.
name.
Hello, sir. Sir, I got disconnected. So could you just repeat the answer?
Who?
Previous one. Sir, division.
Divya. You should be doing all 12 yourself. Okay, don't ask me to repeat. But since you are asking, I'm repeating.
Sorry, sir. The thing is that my network is very poor. So
Okay. See, if I have to check, somebody told the answer for change of internal energy. Okay. If I have to check change in internal energy, the only check I have to see is what is happening to the temperature. If the temperature is increasing, internal energy is increasing. If the temperature is decreasing, internal energy is decreasing. Is that clear? In the AB process, nothing is happening to the temperature. Why? Because it is isothermal process. It's neither increasing or decreasing. Therefore, the internal energy is not changing. It's zero change of internal energy. Is that clear? Similarly, to identify work, you just have to check the volume. If it is increasing, it is positive. If it is decreasing, it is negative. So, anybody?
Sir, could you repeat what adiabatic process was?
Adiabatic means when heat is not supplied to the system, neither taken from the system. In very simple terms, I'll not write it when because it is there.
Sir, so like what's the difference between that and isothermal?
Isothermal is temperature doesn't change. Always when you supply heat, it doesn't change the temperature. Okay, temperature and heat are two different things. I hope you know it. Okay,
Yes, sir.
I'll give you a very simple example. Suppose I pull the piston up. Pull the piston up. Okay, piston goes up. What happens to the temperature? When volume increases, temperature decreases. Okay, get the point? Is that clear?
Yes, sir.
I will pull it up, the temperature can go down. Now, if I supply heat and pull the piston up, heat can increase the temperature, but pulling the piston up can decrease the temperature, and hence the temperature may remain same. Is that clear?
Yes, sir.
So that's an example of heat not changing the temperature. In thermodynamics term, whatever heat I was supplying, that much is the work done by the system, and internal energy is not changing. Is that clear? That means temperature is not changing.
Yes,
That
sir.
would be like a very super cool machine. Okay, so it's not like that easy to develop that I'm supplying and the thing is going up. So going back to the question. Yeah. Yeah, anybody out of the 11 left out, anybody wants to pick one and say?
Sir, work done between A and B is positive and B and C is positive.
Only one. Okay,
Work
W1.
done between A and B is positive.
W1 is positive, he says. What's your reason? And what's
So
your
because
name?
volume is increasing between A and B.
Yeah, volume is increasing, so work is positive, as simple as that. Okay, that piston is moving up. Work done by the system is positive, volume is increasing. Is that clear? As simple as that.
Sir.
So, anyone can comment on Q1? Anybody on Q1? Jaldi bolo, jaldi, we'll have to end the class now.
Q1 was positive.
Name. Name of the boy who said the previous answer.
Sir, Ishan.
Who? What?
Ishan.
Ishan. Okay, so Ishan will not say another answer. Before that, the girl who said internal energy change is zero.
Sir Janvi.
Janvi. Okay, next, who wants to pick up? Anyone?
So Q1 is positive.
Q1 is positive. Absolutely right. Reason?
So it's the sum of the internal energy and work done.
It's simply addition of the two. So that is what you will be doing. You'll figure this out, and just add it up. Is that clear? So 0 plus positive must be positive. Is that clear? In very realization kind of terms, that is, I'm supplying some heat, internal energy is not changing. That means the system must be doing work. Okay, that means you're totally understanding how the piston and things are moving. Otherwise, simply looking at the numbers over there, 0 plus positive is positive. Okay. Now, next one, what's your name? Who said this? What's your name?
So Anika.
Nika.
Anika.
Okay. Next,
Sir, is Q2 0?
name?
Ranan.
Raghav. Okay. Why do you say U2 is 0?
Sir, because you said it's an adiabatic process where there's no change in heat.
Absolutely right. Okay, because it's an adiabatic, that means Q2 is 0, that's the easiest pick. Okay, so Raghav. Full points for picking a very easy one. Okay, next. Anybody? Are there 12 people in class?
So W4
Uh,
is 0.
What?
I was gonna say the same thing.
One second. How many people are there?
There are 9.
9 people. Okay, at least 9 answers. Just hiding it. Okay, who's the next one?
So I was gonna say W4 is equal to 0.
What?
W4 is equal to 0.
W?
4.
4. Okay, who are you?
Sir, Divija.
Divija.
Yes.
Okay. Divija.
Yeah.
Okay. W4 is equal to 0 because volume is not changing.
Yeah.
Everybody agrees? Okay, next one. So 9 of you together is as good as one teacher. Okay, next one. Anybody?
So W3 is negative.
Name.
Anika.
Name should not be here. New name. Are there other names at all? Or they just there? Is anybody else in the group?
There are 4 more people.
Are they there or it's just logged in?
Sir, W2 is positive.
Name?
Smritik.
W2. W2, where is W2? Yeah, W what? W2. Oh, 2. Yeah, W2 is positive. Why do you say that?
So change in volume is positive.
Yeah, okay. So who will say delta U2 is what? Now anybody can speak, even the names possible over there. Delta
So
U2 is what?
negative.
Sir, negative.
Negative.
Yeah, it is negative. Why? Because Q is 0. So it is 0 because of this reason also, and it is negative because temperature is reducing, right? We just had a bit of reading on the temperature. It goes this below the isotherm. That means temperature is reducing, right? Now, next one, these 3. Yeah, guys, you can repeat, okay? Those who have already spoken can repeat. I cannot quote the others more than
W3
this.
is negative.
W3 is negative for sure. Delta U3,
U3 is positive.
Q3 is positive.
what? Delta U3?
So Q3.
U3 is the last thing I would hear. What about
Okay.
U3?
So delta U3 is 0.
U3?
Delta U3
Yeah.
is 0.
Oh, very good. So you think that this temperature and this temperature is same. That means you
Yeah.
think that the P into V over here multiplication and P into V over here multiplication is same. Like why on earth? When P is same at both places and the V's are so different, why do you think the temperature is same at both places? Why on earth? We just did a while back. In the PV diagram I showed you. That this, compare this to this, compare this to this, compare this to this. That time people were answering. Among all of this is the lowest temperature. Low P, low V. This is the highest, what looks like. High P, high V. How can this temperature and this temperature be same? So there must be something going on in your head when you say same. So just
No, sir.
flush it out.
Sorry, sir. I was taking something. I'm so sorry.
Yeah, but still, why do you think it was same? Like, what goes on in your head?
No, I read this chapter from somewhere. I remembered wrong. I'm sorry.
Don't remember, man. If you try to memorize anything, it is so many things that after 2 years you'll not remember anything. Read it as it is. You can't memorize anything. So what do you think is happening? What is
Sir,
the
does delta U3 should be negative? Like it can be positive but less than W3.
Not at all. How can it be positive? Why are you again thinking of as soon as little something comes, no, your mind really starts going here and there. Again, I think you are thinking of something like this, as if you know this. I don't know what you're thinking. I don't know why would you say that.
Sir, it's negative,
You are
right?
thinking of adding something or all. What you have to think? 10 times I've told you, the only thing to think when you are wanting to know what is the change of internal energy, what is that? Did the temperature increase or did the temperature decrease?
So your temperature is decreasing, so it should be negative.
The temperature decrease, there is no doubt about it. There is no doubt about that the temperature decrease. This isotherm is somewhere over here. That isotherm is somewhere over there. That isotherm is there. If you can't draw isotherms in your mind, then at least you know that pressure into volume over here gives you temperature. And pressure into volume over there gives you temperature. Pressure is same, volume is much more at C, then the temperature is much more at C. The definite decrease in temperature without any doubt. Same temperature as C would have been here somewhere, this line would have been same temperature of C all over. This would have been TC temperature, this would have been TC temperature, this would have been TC temperature. But my bigger issue is that you guys are the ones who did not answer and not even thinking in terms of temperature. And that's the only thing you have to think. You start thinking on, okay, this is enough negative, then little positive, will it make it negative or not? Because I know this is negative. That basis knowledge that this is negative, I know, is itself wrong. I mean, that should not be the way of thinking. So do not digress of the right way of thinking. If you don't have the right way of thinking, you may stumble about the right answer at times and may not at other times. Is that clear? Temperature decreases, so this is negative. Now you come to this, and what do you say? Now you'll come to this formula. Okay? Is that clear?
U3 is negative.
Yeah, because both are negative, this has to be negative. Is that clear? Okay, last one quickly. What is delta U?
Positive.
Yeah, why it is positive?
Because temperature is increasing.
Because temperature is increasing. That's the only thing I want to hear. Okay? Get the point? So what is this?
Positive.
Is positive. Why do you say temperature is increasing?
So because in the bottom, like P dash into VA.
Yeah, PV multiplication is more at A, right? As simple as that. Or I have drawn some isotherms in my line and it is clearly going up. Okay? Is that clear? Is that clear?
Yes.
Now, delta U of the whole cycle will be equal to 0 because it comes back to the same temperature. Because TA minus TA is equal to 0. Okay? And CV into TA minus TA is 0. That means delta U1 plus delta U2 plus delta U3 plus delta U4 is equal to 0. If there are some positive U's, then there has to be some negative U's. Okay, in this we have seen only one positive U, which is this one, and two negative U's, right? Is that clear, guys? So based on this, a lot of questions come that you can realize that the total internal energy change is zero or not. Is that clear, guys? Secondly, I'm writing something. Tell me if it is correct or wrong. Q1 plus Q2 plus Q3 plus Q4 is equal to W1 plus W2 plus W3 plus W4. Is it right or wrong? It is absolutely right. Why? Because I'm simply adding
Yes,
the
sir.
law 4 times. Okay.
Yes, sir.
Q1 is equal to delta U1 plus W1. Q2 is equal to delta U2 plus W2. And like that, 4 times you write, and then you add it up. U1 is equal to delta U1 plus W1. U2 is equal to delta U2 plus W2. In this you write and you add it up. This addition will become 0 because total internal change is 0, and you'll end up with this. Is that clear, guys? Is that clear? Is that clear? Is that clear, people?
Yes, sir.
Yes, sir.
So listen to one thing which
Yes,
generally people I would have asked, but since no time is there, I'll just tell you. Efficiency is defined as work, total work divided by heat inputted. Now total work is this, okay? Heat inputted is not this. If I do heat input as that, Q1 plus Q2 plus Q3 plus Q4, then this will always come as 1, right, guys? Right, guys? So efficiency will always come less than 1 because total work is W1 plus W2 plus W3, of which some is positive, some are negative, okay, divided by only the positive Qs, wherever the heat input was positive. Is that clear? So we'll leave out the Q3. Q2 is obviously 0, so we'll leave out the Q3. So divided by which all? Only the Qs which were positive, okay? Is that clear? And therefore the lower number will be larger than the numerator, and hence it will always come less than 1. So that's again a law that there is no cyclic process. There is no cyclic process with 100% efficiency. That means it's not like I mean, there is a incapability of making a good machine and all. The best of machine will not have the 100% efficiency, because in any cycle, it's a law that there will be at least one Q which will be negative by law, okay? By law. So people have spent ages and ages to figure out something which, I mean, defies the law. Is that clear? So that is the session for today. Digest it all, okay? Is that clear, guys?
Yes,
The
sir.
best machine is called Carnot engine on paper. Okay, you cannot make it on paper, where you have isothermal, adiabatic, then again isothermal and adiabatic. One may wonder why this is the best, but then this is the best. And there was a guy called Diesel, he made another which was something like this. Okay. Then there was Otto cycle is there, Diesel cycle is there, which is easier to construct and all, and easier to make the engine. Okay. So the best efficiency is Carnot cycle, which is this one, and you have a certain efficiency for it. Again, it is given by this formula, which can be boiled down to a smaller formula of 1 minus T1 by T2. This is a T1 temperature. This is a T2 temperature. Isotherms. Okay. So since there will be a difference in temperature for the engine to work, there will be a efficiency less than 100. So a lot of theories are there. So that is we'll discuss that some other time. So that's it. If you have any doubt, ask me. Otherwise, bye bye. Don't forget what you have learned today.
Yes, sir. Thank you, sir. Good night.
So
Bye, sir. Good night.
Bye. Good night.
so